Firstly, I shall remind you the definition of the complex integral. Let us consider in the complex plane uh, a- an open set D uh, and a function f, a complex function. Here, uh, a path, a parameterization for this path, a, b, gamma. Here is the starting point, gamma of A up to gamma of B. Here T goes to gamma of T is here. The definition, the integral of our continuous function f along gamma f of z dz is by definition the following: integral from A up to B f of gamma of t times gamma prime of t dt. You know that from school that in the case when the function admit a primitive, we can compute it directly. For example, on the real axis, the case you know from high school, we have an integral, a function f defined a real function uh, which admits a primitive g prime. Then in this case the integral from a up to b f of x dx is g of b minus g of a. Uh, in the complex case, in the case of the complex integral, if g is a primitive of f, that is f is g prime, then our integral along gamma f of z dz, instead of f, we can put g prime, integral from a up to b, g prime of gamma of t times gamma prime of t dt. And this expression can be written as integral from a up to b, the derivative with respect to t of g of gamma of t dt. So a primitive for this integral is g of gamma of t, and we have to consider this for t from a up to t equals b. And that is, we get g of gamma of b minus g of gamma of a. Very similar to the case you know from high school, but in this case is the value of the primitive at the end point minus the value at the starting point. I shall, uh, this is very, very similar. Now, uh, a very particular case of path is the constant path. Uh, Definition, a constant path in a set D is a path of the form gamma from an interval AB to D, gamma of t equals a fixed point z0. This is a fixed point. So the image of this path is just a point. In this case, in the case of a constant path, integral along gamma of f of z dz will be integral from a up to b f of gamma of t times gamma prime of t dt, but this is 0, so the integral on a constant path is 0. We shall remind also the case of closed path. Remark in the case of a closed path gamma from AB contained in a given set D that is a path such that the starting point coincides to the end point. In the case of such a path, if there exists a primitive g, then the integral along gamma f of z dz, which you know is in this case g, the primitive, the value of the primitive at the end point gamma of b minus g of gamma of a, but here we have the same point is 0. Here this case in a set D, this is a closed path. The starting point gamma of A equals gamma of D, described by using gamma. So the existence, if here is our function admits a primitive g, then the integral along a closed path is 0. Let us now compute the integral of a function along a closed path. Let us consider the following exercise. Let us consider the following function. Let f defined on C minus I complex function defined in the following way: f of z equals, I shall let it depends on certain parameters, let a minus 2 over z minus I squared plus a subscript minus 1 z minus I plus a0 plus a1 z minus I. This is our function. Here it is, in this case, the open set, the domain of definition is complex plane without the point I. This is a holomorphic function, and let us consider the following path. let us consider the following path. Gamma. Here is I. This is circular path. The starting point is here. And we wanted to, in our exercise, we have to compute integral along gamma of our function f of z dz. Solution. Integral f of z dz along gamma is we can write in the following way: a minus 2, this constant, times integral along gamma 1 over z minus I squared dz plus a minus 1 integral along gamma 1 over z minus I dz plus a0 plus a0 integral along gamma dz and plus a1 integral along gamma z minus I dz. You can remark that this integral is 0 because this function admits a primitive on the set D. So integral along gamma 1 over z minus I squared dz is 0 because 1 over z minus I squared. This is the derivative of minus 1 over z minus I. So admit a primitive. In a similar way, integral of dz is 0, a similar reason, and the integral along gamma of z minus I dz is also 0 because in this case z minus I is the derivative of z minus I squared over 2 derivative of this here because here the function is 1 is the derivative of z minus I, we can put in this. So let us denote by I the integral we have to compute. It remains to compute our integral is it remains here a minus 1 times integral along gamma 1 over z minus I dz. This function does not admit a primitive on a domain containing the whole image of our path. The function is defined on D, but it does not admit a primitive on this set. It is necessary only on a subset, but there isn't a primitive on a set containing the image, the whole image of the path. So we shall compute this integral by using a parametrization, the definition. Let us describe this path. I shall consider again here. This is our path, I. a parameterization for this. We can use the angle for a t here, angle. So we start from minus half of pi up to 3 pi over 2 gamma of t equals exponential of I t. No, it is translated is I plus is the unit circle translated exponential it. You can remark that here it starts from 0 and the endpoint is also 0. So our integral will be a minus 1 integral from minus pi over 2, 3 pi over 2. And we have here to substitute this 1 over the definition. You know the definition. Instead of this, we put I plus exponential of it. And we have minus I times the derivative of gamma is I exponential it dt. This 2 cancel, we can simplify, and the length of the interval is 2 pi. So we get 2 pi a minus 1. This is the value. It depends only on this coefficient. Remark, this formula f is directly f function. F is given directly expanded in a Laurent series around the singular point I. The missing terms have the coefficients 0. And so this coefficient a minus 1 is exactly the residue at point I of f. So our integral is 2 pi residue at I of f. Here you can see the idea of the theorem of residue, one of the ideas which is based on the theorem of residue, this example. Now we need some definition in order to present the theorem of residues. Firstly, we have to define the winding number. Let us consider here a path, a very complicated path. For example, this is the path. It is a closed path, gamma, AB. This is the path gamma. And now, for example, if we consider this point Z0, the winding number, index number, also called with respect to Z0 of gamma, is 1, because gamma winds just one time around the Z0. the number of turns gamma makes around Z0 is 1, but for this point Z1, the winding number of Z1 with respect to gamma is 2. Around Z1, gamma one turn and another turn. Here, for a point Z2, in this, for the points in this area, gamma make a rotation, just one rotation, one turn around Z0, but in the inverse sense of the trigonometric. So the winding number of Z2 with respect to gamma is -1. For a point Z3, Z3, the winding number with respect to Z3 of gamma is 0. 0 turns around Z3. For all points in that area, gamma makes 2 turns around this point in that area, just 1, here -1, and for the points outside the winding number is 0. Now this is the winding number. How many turns around the considered point gamma makes. Now we need another definition. Here, let us consider two paths with the same endpoints, gamma 0 and gamma 1. With the same, we can use the same interval by a change of parameter. This is not important. And this is gamma 0, gamma 1. And here is a set D. We say, definition, we say that gamma 0 and gamma 1 with the same endpoints are homotopic inside D, homotopic inside D, in D, homotopic in D, if one of them can be continuously deformed into the other inside D without leaving D. If one of them can be continuously deformed into the other inside D. Very important, inside D, without keeping D. For example, in the case when this is the set D, but this area does not belong to D. For example, these paths are not homotopic in D. Gamma 0, gamma 1, not homotopic. And gamma 1 are not homotopic in D. It is not possible to deform the gamma 1 into gamma 0 inside D. This point does not belong to D. Now, another definition. we say that the closed path gamma is homotopic to 0 in D, homotopic to 0 in D, if gamma can is homotopic to a constant path in D. Let us present such a situation. Let us consider the set D. Here, this point does not belong to D. This closed path is homotopic to 0 in D. It can be continuously deformed into a point, but the same set, this path is not homotopic, gamma not homotopic to 0 in D. D is this set, this point does not belong to D. We cannot deform continuously into a point this. Another example, the unit circle with the center, the origin. Another example, yeah. The unit circle is homotopic to 0. Let here is I. No, not I, 2I. I is here, 1. Gamma, this homotopic to 0 in C minus the point to I. We can deform this path continuously into a point without passing through this point, but the same path is not homotopic to 0 in C star. C star is C minus 0. If this point is eliminated, then we cannot deform continuously this path into the constant path 1. Now, the theorem of residues. Theorem of residues. If D is an open set, F from D to C is a holomorphic. That is also called C differentiable function, and S is the set of all the isolated singular point of f and gamma from AB to D is a path homotopic to 0 in the set D, the union of D and S. Then the integral along gamma f of z dz is 2 pi I sum for z belonging to S, the winding number of z with respect to gamma residue at point z of f. This is the formula of residues. Let us present an example, the following exercise. Let us consider the following path. Here is again I, and we consider the following path. Under the function f having a singular point, isolated singular point 0 and I, f from C minus 0 and I to C, f of z equals 1 over z squared times z minus I. Compute integral along gamma f of z dz. Now here the solution. We use the theorem of residues. In this case, the set D is C minus 0 and I. This is evidently an open set. For each point you can find a disk contained in this, the singular point. The isolated singular points in this case are 0 and I. And the winding number now. Winding number with respect to I of gamma is gamma one term, but an additional term is 2, and winding number with respect to 0 of gamma is just 1. So we get integral along gamma f of z dz is 2 pi I. We have just two isolated singular points will be the winding number of 0 with respect to gamma residue at point 0 of f plus winding number of I with respect to gamma residue at I of f. We 2 pi I. This winding number is 1, so it's the residue 0 of f plus this is 2 times residue at point I of f. Here for our function f of z is 1 over z squared times z plus z minus I. You can see that in this case z0 equals 0 is a pole of order 2, the second order root of this expression, and z1 equals I is a pole of order 1. We have already presented formulas which you can use in order to compute these residues. We now stop here. Thank you.